Here's a review for test number 1 for 476-676 Advanced Embedded Systems. Now, the format for test number 1, you're probably going to get about 5 questions, 1 or 2 on hardware, the rest on Python programming. Test number 1 is available in person or on Blackboard. In person, you get 1 class time, 50 minutes. You can work on the problems in any order, go back to old problems. On Blackboard, it's 100 minutes, questions presented in random order with no backtracking, meaning you have to submit problem number 1 before you go on to problem number 2. That's kind of a disadvantage for the people on Blackboard, but I kind of have to do that because otherwise tests wind up on Chegg, people work together. Not supposed to do that. This is part of the way I make sure that people are working alone. In terms of the content, you'll have hardware and software. On the hardware side, if you look at binary inputs, the Pico reads 0 volts as logic 0, 3.3 volts as logic 1. You can convert hardware to those logic levels with push buttons or voltages. If you have a push button, I can use a pull-up resistor or pull-down resistor. In the first case, if I have a pull-up resistor, when the button is not pushed, I read logic 1. When the button is pushed, I read logic 0. That's kind of how your board is set up. You could set it up with a pull-down resistor with the button tied to 3.3 volts. In that case, pushing the button gives you logic 1, releasing it gives you logic 0. We actually do the former just because logic 0 is ground, that's pretty clear. Logic 1 is not necessarily so clear. Is that 0 or 3.3 volts, 5 volts, 12 volts? Depends on the processor. With the Pico, if you hit it with 5 volts or 12 volts, you fry the Raspberry Pi. So this is safer. You can also convert voltages to logic levels. That's typically done with a comparator. If I take a comparator, like a 602 op-amp, I can power it with 3.3 volts and ground. And that way, if V plus is more than V minus, it slams high, 3.3 volts. If it's less than V minus, it slams low, 0 volts. So I can compare voltage. Is the voltage greater than 1.73 or less than 1.73? So this gives the logic the voltage is, misspelled it, is less than 1.73 volts. And it doesn't have to just be voltage. If I make this a resistor, I'm finding out is R less than some value. If that's a temperature sensor, is T, in this case, greater than some value. Light level greater than some light level. That'll give you binary outputs, 0 volts, 3.3 volts. In terms of binary outputs, there's a couple ways to do it. On the Pico, 0 volts is logic 0, 3.3 volts is logic 1, and the Pico is capable of sourcing or syncing up to 12.5 milliamps. If your load needs less than 3.3 volts, less than 12.5 milliamps, I can drive it directly with a resistor. Pick R to set the current. In this case, it's going to be 3.3 minus 2 over R, gives you 10 milliamps, solve for R. If I need more than 3.3 volts or more than 12.5 milliamps, I can use the transistor as a switch. In this case, when I turn it on, and this is 3.3 volts, it turns on. Ideally, this saturates at 0.2 volts. I've got my voltage going to ground, motor turns on. When the Pico outputs 0 volts, that turns off the transistor. No current, motor's off. So this will turn you on and off in one direction. If I want to have 2 directions, forward and reverse, I could use an H-bridge. So in your kit, there's an H-bridge. You've got, actually this is a dual H-bridge, 2 inputs, input 1, input 2, control out 1, out 2. The second one, in 3 and 4, control output 3 and 4. So with this I can make the output go plus voltage, minus voltage. Well, plus voltage would be 1, 0. Minus voltage would be 0, 1. And off is 0, 0 for 2 inputs. For analog inputs, the Pico has an onboard 12-bit A to D that reads 0 to 3.3 volts, and it reads it in as 0 to 65,000. That's part of the machine library. If I want to read a different voltage range, something bigger than 3.3 volts, I can scale it down. For example, 0 to 10 volts can be scaled down by using a divide by 3 circuit. If I want to convert a different range, like plus minus 10 volts, what I can do is rewrite it as y equals ax plus b times 3.3 volts. Add a third term, c times 0. What that c does is to use this resistor circuit, a, b, and c have to add to 1. If that's the case, then c is whatever it takes to make everything add to 1. The resistors are just scaled. Pick your favorite resistor value, like 10K. Ra is your 10K divided by A, its scalar. Rb is R0 divided by B scalar, and C. So by using just 3 resistors, in this case I can convert minus 10 to plus 10 volts to 0 to 3.3 volts. For analog outputs, there's a couple ways to do it. The simplest with the Pi Pico is to use PWM. PWM is part of the machine library, and with it I can output a binary waveform that's either 0 or 1, 0% to 100% of the time. With that, I can drive a motor. If it only goes positive, drive a motor LED just using a transistor. If I want to go forward and reverse, I could use an H-bridge. Another way to do that is to use analog outputs. That's something that's covered in ECE 320 electronics. Different course, not on the test. That's on the hardware side. On the software side, we're programming everything in Python. Python is very much like MATLAB. If you're used to MATLAB syntax, you're pretty much used to Python syntax. It has addition, subtraction, multiplication, division, works with real numbers, works with complex numbers, does logical operations and or exclusive or not. Really friendly piece of software. In Python, you have loops. There are for loops, while loops, if statements. The note about Python, though, is the start of a loop is signified by full colon, and indentation is important. What the indentation tells you is this is everything inside the loop. Once I remove the indentation, the loop is done. I can also do nested loops. If I have indentation followed by more indentation, this is a loop inside a loop. That's a nested loop. If I bring this one back out, those would be separate loops. Plus you have while loops, if statements, else if statements, else statements. Syntax is slightly different, but same idea as MATLAB. In Python, you have subroutines. Subroutines are defined by the term DEF. That's your definition. With a subroutine, I can pass 0, 1, or multiple terms. Here I'm passing 2 terms. When I return, I can return 0, 1, or multiple terms. For example, here, I'm returning 4 terms. When I receive them from the main routine, I can receive them as a single variable. That'll show up as an array. Or I could say ABCD is operate that returns them as 4 different variables, ABCD. In order to access binary inputs and outputs, that's where you use the machine library. In machine, there's the function pin. Pin lets you declare a function to be input or output. For example, here, pin 15 is declared as an input with a pull-up resistor. I can then read it by doing button.value. I could set up a pin to be output. If I do pin 16 is output, I can then write to it, and the options to write are you have toggle. There's also led.value. I can say the pin is off, led.value of 1, pin is set. I have 3 options, set, clear, toggle. In terms of programming, I can use binary inputs to control program flow, and there's kind of 2 different versions. There's level-sensitive programs and edge-sensitive programs. A level-sensitive program was like the debate moderator. While I'm speaking, my time is running down. While I'm not speaking or listening, my time stays constant. As long as I'm at logic level 1, something happens. That's a level-sensitive program. An edge-sensitive program is instead to look for the rising edge or falling edge. For example, a voting machine. Every time I see a rising edge, I'm going to add 1 vote to candidate A or candidate B. And there are several techniques for detecting edges. For analog inputs, the Pico has a 12-bit A to D built in. It's part of the machine library. To use it, I have to import ADC from machine, set up the pin they're using. There's analog input 0, 1, there's also 2, 3, and 4. 4 is the temperature of the Pico. To read it, I would do read 16, read U16. That's going to give you the number 0 to FFFF. 0 is 0 volts, FFFF is 3.3 volts. For analog outputs, there's several ways to do it. Probably the easiest is to use PWM. That's also part of the machine. With PWM, I have to tell it which pin I'm going to be using, set up that pin as a PWM output, set the frequency of the PWM, and then the duty cycle. The duty cycle again goes 0 to 100%. 0 is 0. FFFF is 100% and proportional in the middle. There's also a nanosecond version that lets you specify the pulse width. In terms of measuring time, that's part of the time library. I can record the time since reset by using the ticks millisecond or tick microsecond. I can pause using the sleep command. For example, if I want to know how long a routine takes, I can say how many clocks have gone by since power up before I call the routine, how many clocks have gone by at the end, take the difference in the two, that's the time elapsed. The tick microsecond actually takes a little bit of time, so what this code does, it also measures the time of tick microsecond, subtracts that from the calculations. So a sleep command is about 1 million clocks. It's actually 1,000,004 when I ran it. I can measure pulse width. That's part of the machine library. That's the time pulse microseconds. So if there's something coming in, I can measure the time of the pulse. I'm going to set up pin 17 as an input with a pull-up resistor. And I'm going to print so here's your pulse, how long the low section was, that's right here. How long the high section was, that's this column. That's what the 0, 1 does. What's the pulse? The duration of the low pulse. What's the duration of the high pulse? The 500,000 says if I don't see a pulse, time out after 500,000 microseconds, half a second. And lastly, we looked at SPI communication. This is one way to talk to various devices using the SPI protocol. SPI has 4 lines. There's chip select, clock, master out, slave in, master in, slave out. What the chip select does kind of varies with the different devices. On a latch, I throw the latch. On other devices, I bring chip select low, telling the device I'm talking to you. The clock line chirps in your data, and it can be the rising edge, falling edge, clock idle low, clock idle high. There's various versions of it. On this one, the clock is idling high. I read on the falling edge, shift on the rising edge. Now to do that, I can use bit banging, basically control the pins one by one. Clock is an output, QH is an input. I can read the data one by one, or if this is master out, I'm writing to it, I can set the data bits as I clock them in and out. All controlled by software. You can also do that via hardware using the SPI function in machine. So those are the topics that are fair game on the first test in 476. Again, 1 or 2 questions on hardware, the rest on Python programming.